Hello everyone, I'm Mindili from GIST. We will talk about the operational amplifiers in this chapter. The ideal operational amplifier has the following characteristic as we had learned in the undergraduate course. Its voltage gain is infinite, and we also have infinite bandwidth and infinite G-in and no offset and no noise and zero output impedance. In the symbol we had like a plus and minus, and the output is like amplifying the input difference. So the output is voltage, so it looks like a voltage controlled voltage source. It has a two terminal, and take the measure of the input voltage difference and drive the voltage output, AV times V in. So AV here is the infinite, so the AV equal infinite gain. So as you can see, it for the ideal, since the output is voltage source, its output impedance, like for an ideal driver, for the Thevenin equivalent circuits is R out is in the series with the voltage source that should be equal to 0, right? The reason is for any kind of a load we will get the desired voltage gain, right? If the output impedance is the finite, then you will get the different voltage output, right? Because if you have a RL like a different load condition, you will get the voltage division out of this kind of amplifier. So we want that the ideal amplifier, we want to have a R out equal to 0. But in most of the case, for capacitive load, the operational amplifier is often called OPAMP. What it means that even with R out is not 0, still we can get the high impedance. Let's say R out is finite, then if the capacitance load is there, we will get the still large voltage gain. So at the DC, so in that case the DC gain is maintained regardless capacitive load size. For that case, we call it OTA, operational transconductance amplifier. We will see that it's a symbol. The following is the operational transconductance amplifier. It's a symbol like this. You take the difference, and then its output is now the current, like a right? So GM times V in. We have a finite transconductance. In typical transistor, its current direction is like going down, for example, right? You take the input difference, right? V in, you get the GM VI in. So let's make it this direction as a reference. Okay, so in that case, what it would have is that the finite, it had the finite transconductance, big GM, and then infinite G in because it's open, right? And no offset at the input. So if the offset is V offset OS equal to 0, right? And there's no noise and also now the output characteristic, output impedance is infinite. So for ideal current source, since the output is in current, so it's current driver. So we can look at it as a voltage controlled current source, right? So we take the voltage input and then generate the current output. So for our ideal current source, we want that to have output impedance infinite, right? So that it's the current output only delivered to the output load condition at the load, right? So this R out should be modeled inside this model. So the R out is modeled equal to infinite in this case, for an ideal case, right? Okay. So voltage gain can be defined out of this OTA, considering the load condition. If the voltage output would be what? V out would be minus GM times V in times R out in parallel with RL, right? So if we know that load condition, we can get the voltage output, thus we get the voltage gain, right? So we will summarize the amplifier topology. So like on these figures, for the triangular symbol, we'll call it like operational amplifier. For the other case, like the OTA, it doesn't have a sharp angle because that one will represent the current output, right? So voltage input to current output. So its gain is transconductance, GM. For the OCA, operational current amplifier, is they take the current input and they generate the current output. So this is the current gain. And the current mode amplifier is the current input and voltage out, right? For each case, we can define the voltage gain from input to output. How? For the amplifier, it has the inherent voltage gain, like just it is given. For the OTA, it can only calculate the voltage gain for given RL cases. Once the RL is given, so we can find the gain AG times RL, right? For the operational current amplifier, if you know the input resistance and the load resistance, we can get the current gain. Think about the voltage gain is found by the ratio between input voltage and the output voltage, right? To find out that, we need that RL condition and also input RS, load RS register, right? So if we know the I in, then we can find out the voltage at the input. For the CM amplifier, current mode amplifier, so if we know the input resistance RS, and then we can find the input voltage and output voltage ratio by having current mode amplifier gain times 1 over RS, right? We'll talk about the single stage operational amplifier. The most simplest operational amplifier is 5TR OPAMP. So here we call it OPAMP, even though the output impedance is finite, because we only consider that the load condition is only capacitive. Okay. Sometimes the people commonly use that term OPAMP, or even with the OTA shown in here, right? In that special case. So this is a 5TR OPAMP. It's voltage input and voltage output, right? And the single stage operational amplifier, here on the right we have the voltage input and voltage output, but we have the differential. So it's a symbol like this. So this is a diff2 single. This is the diff2 diff operational amplifier, right? So for the differential to single-ended, we have a current meter at the load, so we can take the only the single-ended output. Okay, I'm not gonna go ahead reanalyze this thing because we already learned about how we calculate the voltage gain, right? Let's look at the unity gain amplifier structure. For OPAMP shown here, we take the output and feedback to the negative input of the amplifier. Then it is important to identify the range of this amplifier at the input and the output, right? Since this is the amplifier, the negative feedback, as you can see, so if the output goes out and the input goes up, then amplifier output goes up, it follows the output. So the difference between positive terminal, negative and terminal is zero always, right? So for this analysis, you can assume that the input and output will be always the same whenever you make this input voltage changes. For the for input, for example, what is the minimum voltage you can go down? So we have a bottom transistor current source. The minimum voltage we can have for the current source is overdrive voltage, right? And then we also have a same input voltage, so the current always flow the same amount by ISS over 2, right? So such condition we will have a VTH plus an overdrive, right? So assuming overdrives are all same, assume same V overdrive for all TR for simplicity, then we will get what? So overdrive and VTH. And then the minimum voltage you can go down would be what? So VTH plus 2 times V overdrive, right? So one overdrive for the ISS and the other one from the M1. What is the maximum voltage you can go? Is that, so if you go up and up, which one will be first getting into the triode region? So M1 is this node voltage. What would be what? The always VTH plus V overdrive, right? So positive VTH. Then we have this kind of a voltage always there. So maximum voltage you can go up is that this node voltage plus VTH, right? That would be maximum. So that would be VDD minus VDD minus VTH minus V overdrive and plus VTH, right? That would be the maximum input. So the other case, this would be what? So VDD minus overdrive, right? You can look at the output side, the input side, the maximum. Well, that would be the maximum. So what about the output side, the min and max? So for the output side, the same, because the input and output on the left and right, the same voltage by the negative feedback as long as the amplifier is alive. So this is the same minimum. What about the maximum? Maximum also, it follows the output. So if you look at the M4, the maximum voltage at the drain will be what? VDD minus overdrive voltage, right? Across the M4, drain and source, we will have an overdrive voltage drop. That is the maximum for the M4. So this one and that one match as well, right? So we can find out the minimum and maximum range of the voltage for this amplifier configuration to work properly, right? So as you can see, to maximize the output load condition, the range, input and output range, so small VTH would be better, right? And overdrive, right? Or larger range, right? For the OPAMP, single stage OPAMP, the gain of the OPAMP can be found by like, so for V in over 2 and minus V in over 2, for this input, so we get the what? The current flows like that. So this current is replicated through the current mirror. So when you find the big GM at the output, so big GM is what? So this is the GM times VI in over 2. So whole big GM is GM times V in, right? Everything added up, right? This is the half GM V in. So this is GM V in, right? So the R out is what? The RO. R out is ROP in parallel with RON, right? So the AV is the GM times ROP in parallel with RON. So for this simplified gain equation, the similar for this, the cascade amplifier for same V in over 2 and minus V in over 2. So for this input variation, we will get the small signal current flow V in over 2 times GM. So the big GM is the same as before. So the output, when you short the output, so the final, so big GM is the GM, same as GM. And what about the R out? The R out is, right now we have the cascade, right? ROP and R up in parallel with R down. So looking up, the output impedance looking up through the M6 is R up, and the R down is the impedance looking down, right? R down. For the R up is the what? GM RO square, right? In parallel with the GM RO square. sorry, the output impedance is boosted by the cascode, so that will be, so approximately the RO square times GM in parallel with the GM RO square, right? So by having in cascode, you will get the higher gain, right? For the differential amplifier input and output, you can use that thus without load current mirror connection, right? In that case, you can find the single-ended equivalent model. So assuming that this tail load is the common the AC ground, so right, you can simply calculate the input to output voltage gain. That would be similar to the left, right? This kind of a cascode amplifier is also called the telescopic amplifier because we are adding the stack at the input pair on top, right? Directly through the to the VDD. So this kind of amplifier is has the negative point regarding the input and output signal range. So it has very small range, although it has large gain, and typically this is also fast compared to other topology because it's simpler. Let's calculate the input and output signal range. For the unity gain amplifier, we connect the input and output, right? Negative side, connect that, right? So there's a connection here. Now let's find out the range. For minimum lowest volt swing range, so you might think two things. One is that if this input goes down and the output goes down, the bottom transistor may be pushed into triode region. But there's also one thing more considered is that the M4 is also being pushed into the triode region because this drain of the M4 going down. So even before this current source get to the triode region, the M4 will get to triode earlier. So what would be the voltage limit for the output and input? We assume that input and an output is the same, right? For the negative feedback. So the minimum voltage, the output will be VB minus VTH, right? And 4, right? Then if it's going down, and this will be pushed into triode. The other case for the maximum value would be what? If you go up and up, and what would be limited? If this go up, the output goes up, then this X node will push it. So if this go up, the tail load will go up because we have a finite VTH plus V overdrive voltage here always, because we have a ISS is always balanced. The same current will flow on the left and right. And negative feedback, right? Because the input and output voltage are the same, right? The same current will flow through the M1 and M2. So IM1 and IM2 equal. So the same current for the given fixed current will have a VGS equal to VTH plus V overdrive always, right? Now this means that if the input goes up, the drain voltage of the M1 will go up. So it will hit to the edge of the triode and saturation. So that condition will be V overdrive between drain and source voltage will be V overdrive, and also we have the VTH plus V overdrive of the M4. So the starting from the VB, we have a minus VGS, that would be VGS4, and then overdrive of the M2 up until here, the tail source node, and then we go up to the input, that would be plus VGS2, that give us the V in. So that condition would be maximum voltage. So if you the cancel out similar value, that we would get what? So approximately VB minus V overdrive of the 4 would be the maximum value you can get for the signal range. So this signal range is visualized on the right hand side figure. So as you can see, starting from VB reference, it can go down to VB minus VTH, one threshold voltage down, right? And then going up is the up until this kind of overdrive, right? For similar to overdrive for, assuming the VTH for all devices the same, right? We can find out that. So as you can see, the signal range is approximately what? So VTH minus overdrive, right? So this is quite small signal range. So typically this kind of amplifier is not used for the unity gain amplifier structure. So not used small range. In the unity gain and structure. Okay. Let's consider the differential amplifier feedback amp shown on the left. In this case, there is no DC current flow through R1 and all the Rs, so the voltage drop is 0, meaning because there is the capacitive coupling there, so there is no DC current flow through the resistor feedback. So the input and output voltage common mode is equal, right? LCM, they are both equal voltage. Now let's consider that this differential amplifier is implemented with the cascade amplifier, like in this kind of a telescopic amp, OPAMP. As you can see, so here we will just draw the bottom MOS pull down path for simplicity. So because there is no DC current flow R, the voltage at the input and voltage at the output is the same at the bias. So now the question is, so what would be the input and output common mode voltage? The range would be, what would be the range of the common mode voltage? It is similar analysis we had done in the previous the telescopic amplifier. So the input common mode level can go minimum common mode. Input common mode is that VB minus VTH. So if the input goes low too much, then the top cascade will go into the triode region. So that would be the limit. For the upper maximum common mode voltage would be, if you go up, then this M2 input transistor will be pushed into the triode region. So that the actual limit for the common mode range is like this: VB minus. So starting from VB, this voltage drop, and V overdrive voltage drop, and up like that, right? So if you calculate the minimum required voltage drop here and there, so 1 and 2 and 3, then you can find out the range of the maximum common mode voltage. So for the given common mode voltage range, the output voltage swing can only go up and down for the output common mode range. Signal can one side go up and the other side goes down, right? So like this and up and down like a condition. So if the swing is too large in one side, then the cascode device M3 and M4 will be in triode region. So there is also the swing limitation, right? Yeah, there is a limitation of swing. So, and also if the common mode go high, so also there is a limitation. This kind of a swing limitation still presents, right? So for this kind of telescopic amplifier, it has the limited the swing, the common mode range and the swing. So you have to know what would be the penalty or what would be the limitation of your design, right? So you cannot generate or use larger signal than the circuit can support, right? So you have to be aware of well regarding this kind of the requirement. Okay. So the swing range, if you take the difference of common mode level and the peak level, then if you take the difference, then what you get, assuming the similar threshold voltage, then you will get about what the VGS, what it would be. So VB cancel out, so minus VGS minus plus VTH minus VTH, right? Cancel out. So about the VGS of the swing range, the amplitude range you would get, right? So calculating swing range, I was there's a miscalculation. So there, if you cancel it out, then what? So you get the minus VGS 3,4, and the what? It would not cancel times 2 times VTH. Let's say times VTH 1 and 2 plus VTH 3,4, right? That would be approximately what? 1 VTH minus overdrive, right? So that would be the amplitude you would expect in this case, right? For telescopic, there's a simple way to generate the VB cascode bias voltage by having cascode diode connection with a certain current I1. We can generate the additional VGS of the MB1, so that we can generate the VB1 higher than, how much higher? VB1 must be greater than overdrive starting from what? So we have two, so it should be, so the minimum will be, let's say input V in CM, starting from input CM, so minus VGS, right? And plus overdrive and plus VGS. That would be the V1 and VGS2, let's say. that should be the limit. So that would be what, if starting from input CM, so we have a similar VGS, let's say VTH minus V overdrive 2 plus V overdrive of the what? Let's say overdrive of 2, right? Plus VGS VTH plus V overdrive of the P1, right? So that gave us the overdrive cancel, overdrive 2 cancel, VTH cancel, so V in CM plus V overdrive B1, right? So that's the minimum, so we have to make sure that VB1 is well above that this value, right? Okay. So that should be greater than, so VB1 must be greater than, much greater than, right? Like that. Just like make it just greater than, okay? Definitely there should be some margin, right? You have to check the margin in the simulation, okay? So far we had looked at the cascade amplifiers, and we understood that at any time you, as you stack up the devices, your input and output signal ranges becomes more and more limited. So for this, an input and output here, your signal range is limited, right? It's common mode range, right? Range is limited. If you want to have a different range of the input you want to take in, you can fold your amplifier structure as shown on the right here. So you put a current source there and the NMOS changed to PMOS. Then what happened? So for the input range would be near VDD, because we have to set up the VSG here for the PMOS. On the left hand side we have to set up the VSG VGS setup, right, on the left. So that would be VTH plus overdrive voltage, right? So this voltage at bias is near VDD, but for the, if you fold this amplifier structure like this, then you get the what, VTH P absolute plus overdrive voltage, right? So the voltage range would be starting from the VDD. So VDD minus VSG is the input common mode value, right? So we can change your input signal range as you want, right? And what happened to the output signal range? Without changing output signal range, we only change the input signal range by folding this. So obviously the I2 must be I'm sorry, I1 times 2. So we have to flow 2x larger current compared to previous case. For the PMOS input cases, for example here, in this case, your input signal range is near the VDD. The output signal range is below lower near ground. If you want to change your input again, you can fold that PMOS with the NMOS and adding the current source. This current source is also 2x larger, 2x times I1. So folding is kind of a effective way to change signal range, right? Okay. So on the left, the telescopic differential amplifier can be folded. So this input device is folded, right? Along with this tail current source, ISS, right? That changed to PMOS implementation, and then there, this current is what? ISS plus I1, right? So I'm sorry, half of the ISS will have, right, will flow onto here. So half of the ISS 2 plus I1, right, would be ISS 1. So on the left hand side, ISS is what? 2 times I1. So I1 plus I2. So I1 equal to I2. So 2 times I1, let's say. So here, ISS is 2 times I1. So what we have is the 2 times, this is 2 times I1. So this is I1, this is I1, this is what? 2x I1. So half of the I1 here, I1, and it's I1, this is 2I1, right? So you can calculate how much current and for each transistor need to flow at bias condition. Okay. So now this is more complete schematic of the folded cascade amplifier. So here we can calculate the input common mode range. So if the input CM range is that, let's say for the minimum voltage, that would be starting from V overdrive. Here overdrive is the minimum voltage for the X, and then another overdrive here, and then what? VTH plus overdrive. So if you count starting from the ground, you have a 1 plus overdrive, and what? A 2 overdrive, and then minus VGS. So that would be what? So VTH minus V overdrive. And the maximum would be when this device is in the at the boundary of the saturation region. That would be the voltage difference is V overdrive. So starting from VDD minus V overdrive, and then additional minus VTH minus V overdrive. This is the VSG of the M1, right? This is the VSG of the M1. So that would be so what? So approximately, so VDD minus 2 overdrive minus VTH, right? So now the output range is that what? The minimum is that, wait a second, for the minimum voltage is the 1 VH, let's see, it's not the 1 V overdrive plus overdrive minus VTH plus V overdrive. So what you get is V overdrive minus VTH, right? As you can see, this value can even go below the ground level. This is below, so actually this is a very wide range it can cover. So input common mode can even go below the ground, okay? This is very large. And for the output range, it would be, the minimum would be what? So we have a 2 stack of the device, and so 2 times overdrive is the minimum, and the maximum is what? VDD minus 2 times V overdrive, right? We have a 2 overdrive stack. So as you can see, unlike the previous telescoping amplifier, it has very wide range, right? The middle is half VDD. It has a very wide range of input and output column mode, right? And this is widely used for general cases, right? The gain of the folded cascode amplifier can be easily derived by using this equivalent single-ended version of the amplifier. We have the common source. The source node is the AC ground. So our input goes to PMOS, and this will generate the current. So if you increase that, if the voltage go up, then current through this transistor, so VSG will go down, so current will diminish, right? So current flow will go up like this, right? So this current is amount of a current is what? So this is a GM times V in, right? This current will flow here and then up until here. So on the bottom we had the M5 M1 in parallel, so you will get the output resistance in parallel. If this resistor is large enough, then the older current will flow through to the output, right? So if the output is shorted on the right hand side as shown in here, so I out will be what? Just GM times V in, right? So the big GM is approximately, if the RO5 and RO1 is large enough, then GM is approximately GM. Big GM is the same as big GM and small GM. So now if you know the R out by input input is tied to ground, so the output resistance, output impedance we are seeing is M5 and RO1 in parallel, right? M1 we had the RO devices here, RO1. So on the bottom we had the M5 current source. So that one is modeled here, right? So for this kind of circuit, we can find that R down, right, RDN, and R up, right. The RDN downside impedance is what? So this is the source degenerated output resistance, right? That would be RO5 in parallel with R1 plus 1 plus GM 3 times RO3 this is the RO3 plus GM times RO3 times RO5 parallel RO1, right? This is something that you would get for the R down. For the R up is what? So we had the M9 and M7, RO7 and RO9. So RO9 plus RO7 plus GM, ROP and RO9 and 7, RO9 and 7, something like that, right? So we will get like this output impedance. So it becomes roughly the RO up and down are determined by those two factors. So once we know that GM and R out, so finally the R out is R down, in parallel R up, right? So the AV is now what? So GM we found is going out of that, so minus big GM times R out, so that would be so minus GM times R out, so R up and R down, right? And that would be the output voltage gain. So far we just assumed that the R05 and R1 is large enough, right? Much larger than what 1 over GM3. So impedance looking up is 1 over GM3, and looking down is R05 in parallel with R1, right? 1 over GM3. The older signal current flows through M3 rather than flowing into this R05 and R1. So for this simplification, we can get the gain easily. The exact calculation would require the current division through the R5 in parallel R1 and M3 current, but that's not that important. What we can see from here, by the folding amplifier, folded cascode, we can get the same large signal gain as we had in telescopic cascode amplifier. Okay, this is more detailed realization. So for the current source we had is M1, and then the input side tail current source, and then we also have a cascode side, we have a bottom current source and top current source. So when you look at the circuit, you have to identify what is the current source at first. So if you have a current source and at the top and bottom at the same time, this requires always the common mode feedback, because the current source impedance is so high, and so we would have a large output impedance, right? So if there is any mismatch current flows between pull up and pull down, a slight mismatch will cause the output common mode voltage going up and down. So we have to have some kind of a way to take out the output voltage here and then extract the common mode voltage. They use that common mode to adjust either one of the current source, 1, 2, or 3. We have to adjust the current level so that the output common mode is at the desired level, right? So we have to make sure that desired output level with reference voltage is supplied. Typically this is it will be around the half VDD, right? So this output signal we have to control either current source 1 or 2 or 3, right? So this is more things that you have to study. What kind of a common feedback circuits are there, and you have to understand what is the limitation of each cases, right? Folded feedback amplifier is used, for example, used in this circuit topology again, different from the telescopic. We had the large output signal swing range, and also we have large input common mode range. So this supports the large signal range, right? Supported, right? The signal range, and also, right, the input common mode as well as the output COM mode. But for the output COM mode, we would like to maximize the output swing, so we would get the half VDD as the output COM mode. Right? We have a up and down differential signal. The half VDD might be the optimum output COM mode. And for this circuitry, because the feedback resistor had the 0 voltage drop because no DC current flows through, right? So output COM mode voltage will be same as the input COM mode. But for this input COM, this circuitry for this folded amplifier structure, its input COM mode can be easily supported, right? For the half VDD input COM mode would be good enough, would be fine, right? We already showed that what would be the limitation of the input COM mode, so I'm not going to talk again. So half VDD input output CM is well supported. Again, there is no CMFB shown here. There must be CMFB circuitry, so we have to take out the output and let's say X and Y and some reference reference voltage. We would like to put the COM mode to half VDD. So to do that, we have this COM mode feedback need to be there. So we are gonna see how we can implement those COM mode feedback circuit in the next the lectures. Okay, we will stop for now.